So the area of my research is holomorphic symplectic geometry, and this is the complex analog of real symplectic geometry. And I want to give a kind of overview of the subject today, and I'm going to start by describing where these holomorphic symplectic manifolds sort of fit into the geometric landscape, and then say some things about, we'll give some more specific definitions of holomorphic symplectic manifolds, irreducibility, give some examples, and then I'll start to look at fibrations on these manifolds. Okay. So to begin, if we start with a compact Taylor manifold, and if we have a compact Taylor manifold with a trivial canonical bundle, then by Yale's theorem there's a Ricci flat metric on this. Or in other words, trivial canonical bundle or vanishing first Chern class. So then there's by Yale's theorem, okay, so more precisely in each Kähler class you can find a Ricci flat metric. So it has vanishing Ricci curvature, and in this situation the vanishing of the Ricci curvature is really the vacuum Einstein equations. So these are the so I guess more precisely, Einstein equations would usually be in Lorentzian signature. So this is the Riemannian version of the Einstein equations in a vacuum. Okay, so these equations are sort of widely studied in Riemannian geometry, and in particular. This result from late 70s tells us that whenever you have a manifold with vanishing first Chern class, then you have a Ricci flat metrics on that. And so also these manifolds are very important in string theory and rise in lots of different contexts in physics. Now to get a little more precise into the geometry of these things, we can try to decompose it as a product of manifolds. And so in this direction we have the Bogomolov decomposition theorem. And I mean, this is really a result in Riemannian geometry because you use the Riemannian metric on M to prove this result. And it says there's a finite unramified cover of M which decomposes into a product. So let's call it, say, M tilde. It decomposes into a product of just a flat torus. So this would be a complex torus. Then irreducible holomorphic symplectic manifolds, which I'll define shortly. And then Calabi-Yau manifolds. Okay, so Calabi-Yau manifolds here means that these are manifolds with trivial canonical bundle, but with no other differential forms. So I want you take the differential forms on one of these. This will be 1 if I is 0 or the dimension of y, and 0 otherwise. Yeah, I'm about to define. So yeah, this is the partner. This is the main topic: holomorphic symplectic manifolds. Yeah. Okay. So this is where these spaces arise, and now let me tell you what they are. So this, yeah, because I mean this tells you have a if this is 1 when you have dimension y, so you have a trivialization of the top exterior power. So you have the trivialization of the canonical bundle. So, was there something you're concerned about?
I don't remember exactly the definition I saw for Calabi-Yau, but it didn't look like this. So this is why I'm wondering. Is it equivalent? Or
there tend to be some slightly different definitions depending on. I mean, if you just say it has trivial canonical bundle, well, the whole thing we started with has trivial canonical bundle. So more precisely, these in this context, this is a decomposition as a Riemannian manifold, and you can talk about the holonomy of the metric, and so here I want the holonomy to be SUN, where n is the dimension of this thing. Okay. Now. You could do things a little more generally and say the holonomy is contained in SUN, and then you would allow things slightly more general than this, perhaps. Okay. Right. So let me get back to the definition of a holomorphic symplectic manifold is a compact Kähler manifold X, which admits a non-degenerate holomorphic 2 form. So what does non-degeneracy mean here? So non-degenerate means, well, the 2 form gives a pairing on the tangent space, and you want that to be a non-degenerate pairing at each point. Another way of saying that is that the sort of top power of this form is nowhere vanishing. So this trivializes the canonical bundle. So here n is the half the dimension, so the dimension complex dimension of X is 2n. Or equivalently, you could say that this induces an isomorphism of the tangent bundle and the cotangent bundle. Okay, so that's non-degeneracy of the form. So it's sort of the complex analog of a real symplectic form. We have the non-degeneracy, and this will be closed by Hodge theory because we're on a compact Kähler manifold. The holomorphic form will also be declosed, just like in the real symplectic case. Okay, so what are some examples of these? Well, almost by definition, a K3 surface is an example of one of these. K3 surface. And for example, a K3 surface, well, there are many ways of writing down a K3 surface, but you could take, say, a quartic surface in P3. So generic smooth quartic will be a K3 surface. And what does it mean to be a K3 surface? Well, it's simply connected and has trivial canonical bundle. Okay, so here the canonical bundle is the holomorphic 2 form. So if that's trivial, any trivialization of that will give you your holomorphic 2 form. They also have other examples, T being any even dimensional complex torus. And in this case, there are generally lots of choices of holomorphic 2 form, holomorphic symplectic form.
Kähler manifold, does it have a symplectic structure?
Yes, but that's different.
You want it to be holomorphic?
This is a holomorphic 2 form. So the Kähler form would be a 1-1 form. This is a 2-0 form. Or Kähler form would in fact be a real valued 1-1 form. This is a holomorphic complex valued 2-0 form. Actually, I mean that's an interesting aspect which I didn't want to discuss too much. But the real and imaginary parts of this will also give Kähler forms on the space. So you end up with a triple of the real and imaginary parts of this will also give Kähler forms. Actually, I'll mention that in just a moment. Okay, so obviously to get into high dimensions, you could just take products of these as well, etc. These tend not to be particularly interesting higher dimensional examples because they just come from two-dimensional things. Okay, so these are holomorphic symplectic manifolds. Now here I've written irreducible, and so let me describe what that means. So a holomorphic symplectic manifold is irreducible if it's simply connected and the holomorphic 2 form is unique up to scale. Or in other words, the space of holomorphic 2 forms is one-dimensional. So an example of one of these would be given by, it's more difficult to find higher dimensional examples of these. In 2 dimensions, you just have K3 surfaces. And you can try to build them in higher dimensions by taking products, but the product wouldn't be irreducible because it wouldn't satisfy this condition. But if I take a symmetric product, then it's almost what we want, except this will have singularities along the diagonal. But there's a sort of canonical resolution of these singularities, what we call a crescent resolution, which is the Hilbert scheme. And so what is this? This is the scheme parameterizing zero-dimensional length n subschemes of S. Hilbert scheme length n zero-dimensional subschemes. Now, so generically here, a length n zero-dimensional subscheme would consist of just n distinct points, and in general, there's a morphism, the support, which maps down to here. So this is a kind of blow up of the singularities here. Okay, so this produces this will be an example of an irreducible holomorphic symplectic manifold. The holomorphic symplectic form on the K3 surface induces one on here, which pulls back to something non-degenerate up here. Okay. So these are the sort of building blocks of these Ricci-flat manifolds that we saw in the Bogomolov decomposition theorem. And perhaps I'll just mention another connection here to the Riemannian geometry. So again, by Yale's theorem, these irreducible holomorphic symplectic manifolds, because they have trivial canonical bundle there, C1 is 0. And so you have a Ricci-flat metric on these. And the Ricci-flat metric is what we call a hyperkähler metric. Okay, so in other words, the metric is Kählerian with respect to a triple of complex structures. Okay, so this is I is just the complex structure on X, and then there are two other complex structures on the underlying smooth manifold. And G is Kählerian with respect to all of these. And together these behave like the quaternions. They make each tangent space to X into a quaternionic vector space. Okay, so the Kähler forms are then well, in order to get this to apply Yale's theorem, you need to pick a Kähler class, and then you so then you get the corresponding, so this metric, there's already a Kähler form with respect to I, and then the other two are, I can sort of write them combined into a holomorphic two form, and that's this holomorphic symplectic form. So these have a metric, and then it's Kählerian with respect to these complex structures, and then the corresponding Kähler forms for each of these complex structures are omega I, omega j, and omega k.
So the Kähler forms are omega I, omega j, omega k, and
right.
if you do this,
if you combine these, yeah, you get this holomorphic two form. Yeah. So, I mean, really, these are sort of quaternionic manifolds, and but in most of what I say today, we're sort of picking one complex structure out of the choices and just thinking of it as a complex manifold with respect to that one. And in that case, it's a complex manifold with this additional two form. But this is saying that. Conversely, you have a complex manifold with this two form, then you have this whole quaternionic structure on it. Okay. Other questions? Yeah.
Definition of a symmetric product. Is it as a product with the identification of all these combinations, or
just take the product and then quotient by the symmetric group, interchanging the factors. Yeah.
that's what I thought.
Yeah. Okay. All right. So when you have a particular kind of space, in order to study that, you can consider maps to it or maps from that space. So I'm interested in fibrations, which are going to be maps from holomorphic symplectic manifolds. So in some sense, the goal of looking at these fibrations is to try to understand more of the geometry of holomorphic symplectic manifolds. And there's a very powerful result of due to Matsushita, which places very severe restrictions on the kind of fibrations you can have on these manifolds. Okay, so from now, X will be an irreducible holomorphic symplectic manifold of dimension 2n. So if I have a fibration, so by fibration I mean a proper surjective morphism with connected fibers. And I guess I want the dimension of B to be strictly positive and smaller than the dimension of X, which is 2n. Right, so then if I have a fibration on an irreducible holomorphic symplectic manifold like this, then the dimension of B actually has to be half the dimension of the total space X. And secondly, every fiber is Lagrangian. This is with respect to the holomorphic symplectic form. So that means that if we take this holomorphic 2 form, this holomorphic symplectic form, and if you restrict that to a fiber, this 2 form vanishes identically on every fiber.
I have a stupid question. When you say it's morphism, do you suppose X and B is a morphism? Is actually a morphism is a complex manifold, or a morphism is a holomorphic symplectic manifold, or just a continuous function?
As complex manifolds.
Complex.
Yeah.
In fibration, you only require connectedness of fiber. Nothing. The fibers don't have to be the same, or
No, not. It's not a smooth fibration. Just in the sort of in.
you ask local, at least local.
Local triviality?
No.
There might be some singular.
It could, yeah, there will be singular fibers, in fact. Yeah. And a priori, you could even have. A priori, it doesn't need to be equidimensional, but in fact, it will be. Okay, so in fact, it follows from here. Every fiber is Lagrangian, so the fibers are also n-dimensional. And finally, the generic fiber is a n-dimensional complex torus. And then, as I was saying, in codimension 1 over the base, there'll be some singular fibers as well. They occur in codimension 1 over the base.
One fixed torus, or does it vary?
No, it's varying in the family. Yeah. Well, usually it's varying. I guess there are some examples where it's sort of locally isotrivial fibration. Well, all isomorphic to some fixed complex torus. That can happen. Yeah. Okay. So also, it was expected. Matsushita proved some other results about the base of the fibration, and it's expected that it'll be projective space. And Huang proved that if B is smooth and X is projective, then the base is complex projective space of dimension n. So over here, I'm not assuming that the base is smooth. The hypothesis would be, I didn't state explicitly here, but B should be normal, yeah, not necessarily smooth. And also X in general is not projective, but if you study the moduli space of deformations of X as a complex manifold, the projective ones are dense. So you can always deform X slightly as a complex manifold to make it projective.
The theorem says that if you have a map X from irreducible holomorphic symplectic manifold to B, and the B does not have any condition. I mean, you just have map, which you have something like only topological properties, and then you have all this.
Well, no, not topological. This is a morphism of complex. Surjective morphism of complex spaces.
And then it also restricts the dimension of the base space.
Right, yeah.
That's very strong.
Yeah. Okay, so maybe I'll write some examples of these. So the simplest case is for K3 surfaces. Okay. So the only kind of fibration you can have on a K3 surface is a fibration over P1 where the generic fiber is an elliptic curve. And there has to be some singular fibers as well, some sort of degenerations of elliptic curves. So generically you would have 24 rational nodal curves as singular fibers. Okay. Now, in higher dimensions, let's call this S. In higher dimensions, I said we have this Hilbert scheme. This gives a 2n-dimensional holomorphic symplectic manifold. And if the K3 surface that you build this from is an elliptic K3 surface, then it induces a fibration on the Hilbert scheme. So it looks like, let's say, if S is elliptic, then you have a Hilbert scheme. Well, there's already this map down to the symmetric product, and then there'll be an induced map from that to the symmetric product of P1, just because the elliptic K3, that's already a fibration over P1, and so then this is isomorphic to Pn. So here's a map from here to Pn. And this is an example of one of these fibrations. So we call these Lagrangian fibrations, holomorphic Lagrangian fibrations. So the fibers here are going to be just products of elliptic curves. So the elliptic curves are, you already have the elliptic fibers here, and then here you have a product of n of those to give the complex torus fibers. Okay. So a more complicated example is... So now, instead of an elliptic K3 surface, I'm going to take a K3 surface S, which contains a genus N curve. And assume that this is otherwise generic, so that this is maybe this curve generates the Picard group of S. And then so if you have a genus N curve in a K3 surface, its linear system is n-dimensional, isomorphic to Pn. And so I can take the family of curves linearly equivalent to C. Okay, so this is the family of curves linearly equivalent to C. They're all arithmetic genus n. There'll be some singular curves occurring there as well. So each genus n curve is canonically associated to that is its Jacobian, which is an n-dimensional torus. And if you do that, if you take the Jacobian of a family of curves, you get a family of complex tori. So we can take the relative Jacobian. Okay, so we have the family of curves. We just replace each curve by its Jacobian. And this will work okay for the smooth fibers. For the singular fibers, you need to take a compactification of a compactified Jacobian. And then in this space is then a Lagrangian fibration. Okay, so this X here, the total space X, is a holomorphic, irreducible holomorphic symplectic manifold. And this is naturally a fibration by a generic fiber in n-dimensional torus, and it maps down to C, which is the n-dimensional linear system. Okay, so this is called the Wilbur-Chi integrable system. Okay, so I'm interested in these fibrations because I want to use these to study the geometry of holomorphic symplectic manifolds. So the first thing you can ask is when do we have such a fibration? Okay, so the first question is existence. So the simplest case would be in a two-dimensional case. Now, almost by definition, the only irreducible holomorphic symplectic manifolds in two dimensions are K3 surfaces. So you can ask about the existence of fibrations on K3 surfaces. And here there's a theorem. This is, I guess, from the 60s and 70s and due to Kodaira, Shafarevich. And so it sort of comes out of classification of surfaces. Of complex surfaces. So if a K3 surface S contains a divisor D whose square is 0, then S is elliptic. So then S is a fibration over P1 with a generic fiber and elliptic curve. I mean, the converse of this is clear, because if you have an elliptic fibration, then the fiber, if I take a fiber of that, then that will be a divisor on S with a square 0. So in higher dimensions, you could try to think about what the analog of this would be. So if I have a Lagrangian fibration over Pn, and well, so here, I mean, the fiber of this would have square 0. So just pulling back a hypersurface from the base, pulling back a point from P1. Here we'd pull back a hypersurface from Pn. So this contains a divisor D, the sort of pullback of just a hyperplane Pn. And so what property does this have? If you intersect that with itself, if I intersect that with itself n times, well, if I intersect the hyperplane with itself n times, I get a point downstairs. If I intersect one more time, it should be empty. So the analog of this result would be sort of converse of this statement. Okay, so but this is still an open conjecture. So it says if an irreducible holomorphic symplectic manifold X contains a divisor D, whose if I intersect that with itself n plus 1 times and I get 0, then X is, well, I want to say X is a Lagrangian fibration, but in fact that's not quite true. It should be birational to a Lagrangian fibration. So it's known that even if you have, if I have a Lagrangian fibration like this, then you can do birational modifications of X, which wouldn't change this fact. You would still have a divisor with this property on it, but it would upset the fibration, and you wouldn't have a fibration on it anymore. So the best we can ask for is that it would be birational too. But in any case, this is still an open conjecture, so that's what we expect, but we don't have a proof of that in general. So this is being proved in some cases. It was proved independently by Markuszewicz and myself for when the irreducible holomorphic symplectic manifold is a Hilbert scheme of points on a K3 surface. So suppose X is Hilbert and S. So then when do you have this? When do we have such a divisor? Then there exists a divisor D with this condition. Well, this happens. This is if and only if the K3 surface itself contains a curve. Contains a curve C with C squared equals 2n minus 1 K squared for some K, for some integer K. And okay, so then our result then says that in this case, Hilbert and S is a Lagrangian fibration. Okay, so here you get a genuine Lagrangian fibration, not just birational to one. So this is all. I mean, this condition is really a condition on the period of the complex manifold. So it's sort of describing the Hodge structure. Sorry.
S is actually K3 surface, so S is actually K3 surface.
Yeah, S is a K3 surface. Yeah. We need also some genericity assumption here that S is a K3 surface containing such a curve, and then should have Picard number 1, and this should generate the Picard group. So if S starts to contain more curves, then there's more there's more geometry involved, and maybe there's some. This is not quite a Lagrangian fibration. Maybe there's some birational modification or something.
When you say Lagrangian fibration, you're supposed to have a map from this one to have some space. What is the
from this to Pn. From here to, yeah. So it's a Lagrangian fibration of a Pn.
Pn over
Yeah.
Pn.
Yeah. Yeah.
When you say Lagrangian fibration, you always mean over Pn, or?
Yeah. So the result of Huang, the theorem of Huang says the base is Pn if x is projective and B is smooth. Yeah. And that's expected to always hold. We don't know any examples where we have something where the base is not Pn. So, but it's not yet proved in the Kähler non-algebraic case. Okay. So this theorem has been generalized to some, or there are analogs of this for some other examples of irreducible holomorphic symplectic manifolds, and a similar result like that. But in the general case, this is still an open conjecture. This would be very, very useful to know, because it would give if you just take some arbitrary holomorphic symplectic manifold that you don't know anything about, it would tell you, when you have a fibration on that. I mean, you could always deform it slightly to get a divisor like this, and then you would have all this additional structure of the fibration, and you could use that to study the geometry of X. Okay, so I've said that these fibrations are going to contain singular fibers. So I want to say a little bit about what kind of singular fibers.
You can by deforming an arbitrary such a manifold to get a divisor like this?
Yeah, the existence of this divisor is something you can detect from the period of the complex manifold. So for these spaces, we have a kind of local Torelli theorem. You can describe the moduli space of deformations of X in terms of its variation of Hodge structure via the period map. So you can deform X slightly so that a divisor like this would exist. And then we hope that once you have the divisor, that would imply that you have a fibration, but that's still the conjectural part. Okay, so singular fibers. Well, first of all, for elliptic K3 surfaces, or in general for any sort of elliptic fibration, there was a classification of singular fibers due to Kodaira. Okay, I don't want to list all of them, but just maybe describe the first few. So in sort of Kodaira's notation, I have the I1 singular fiber. This is a nodal rational curve. So I guess the algebraic geometry, you would just write it like draw it like this. I guess if you want, but it's really topologically it's like well, I didn't draw it right. A sphere with 2 points connected. Then there's also IN would be sort of a cycle of rational curves. So something like that, perhaps. And then there are, there are some exceptional, well, there's some other sequences and exceptional cases, like, cuspidal rational curve. And you can sort of see these if you take, say, a family of cubics in P2 and you vary the parameter, then you see these sorts of singular curves arising in that family of cubics. I forget what the notation for that one is. So the ones with just nodes are stable curves, sort of stable degeneration. So these ones are these are stable. This one is unstable. And if you have a family of elliptic curves and you have some unstable one occurring, you can do some base change and there's a stable reduction theorem. But generally with these fibrations, we don't want to do base change because that's going to just change the total space we're working with. I mean, base change is something you would use to study things locally. So, I mean, most of these can occur in an elliptic K3 surface. I mean, not all of them because you can't have a cycle which is too large because this would contribute too much to the Euler number of the K3. But most of these degenerations of elliptic curves can occur in a elliptic K3 surface. But generically, we just get these ones. Okay, so generically, nodal rational curves. So generically here means you have a 20-dimensional moduli space of K3 surfaces, and there's a codimension 1 family of those, which are elliptic K3 surfaces. And if you take a generic elliptic K3 in that 19-dimensional family, then we'll have 24 nodal rational curves as singular fibers. So in higher dimensions, various people have studied the singular fibers which arise in a holomorphic Lagrangian fibration. So some people who looked at this, Matsushita, Huang, and Oguizo. And there's a classification of the codimension 1 singular fibers. Okay, so what do I mean by codimension 1 here? So if the base of our fibration is Pn, then there's a hypersurface inside there. And so, I mean, the generic fiber, the fiber above a generic point of Pn is a smooth n-dimensional complex torus. Over this hypersurface, we have the singular fibers. And rise. Well, earlier on I mentioned this Baville-Mukai integrable system, where I took a linear system of genus n curves in a K3 surface, and I took the relative compactified Jacobian of that. So the singular fibers there are going to occur, or the generic singular fibers are going to be, you have this family of genus n curves. In codimension 1, they're going to acquire just a single node. And then I'm going to take the compactified Jacobian of that curve. So if I have curve C with a single node, no other singularities, then the Jacobian of this curve is a C star bundle over the Jacobian of the normalization of the curve. So I have let's say this is my curve C. I have just a single node, then there's some curve C tilde, the normalization of that. And so there would be 2 points here, P and Q, which get sort of glued together to make C. And so why is the Jacobian of this a C star bundle over? It's because a line bundle on here is going to be given by taking a line bundle on C tilde and then identifying the fibers at these points. So I need an isomorphism between the fibers over P and Q. And that isomorphism is given by this non-zero complex number. Okay, so that'll give me the Jacobian of C, but in this family, for the singular fibers I need to take, for the singular curves I need to take the compactified Jacobians. So I need to compactify this C star bundle, and to compactify, what we do. So first of all, this Jacobian of the normalization, this is an n-1 dimensional abelian variety, because this is a genus n-1 if C is genus n. And so over that I have my C star bundle, right? And I can compactify that by adding a zero infinity section and a zero section. Okay, so now this becomes a P1 bundle over this. And then I glue the zero and infinity sections. But when I identify them, I translate as well. So, and what I translate by is all of P minus Q. So all of P minus Q gives me a line bundle on C tilde, degree zero line bundle. So it's really a point in the Jacobian. And when I identify this zero section with the infinity section, I translate. These are both isomorphic to the Jacobian down here. And I have this additional translation. So I sort of glue zero to the infinity section with that slight translation. And so I glue here. And I get something that looks like that, sort of glue that around. So if you sort of cut it this way, it looks like a nodal rational curve. I mean, topologically, it's going to look like a nodal rational curve across an n-1 dimensional abelian variety. But the complex structure is not just a product structure because of this translation. So this is really the I guess the simplest kind of singular fiber that occurs in these high dimensional Lagrangian fibrations. Okay, so that's the simplest one. I mean, more complicated ones would be, what would be the analog of a cycle of rational curves? Would be something that looks like could be some sort of take several P1 bundles over an n-1 dimensional abelian variety and sort of glue them into a cycle like that. Okay, and so on. Okay, so these would be semi-stable degenerations of n-dimensional abelian varieties. And then there are also some unstable ones where you have something like a family of cusps along this locus. Okay. And so this classification includes these examples and then some slightly worse things than this as well. Okay, so I want to say that I want to state as a conjecture here. So over here I said that a generic elliptic K3 contains only the simplest kind, nodal rational curves. I would hope in higher dimensions that we only get these sorts of fairly simple ones occurring as well. Okay, so I haven't really said precisely what semi-stability means here, but things like these are semi-stable and things involving cusps would not be semi-stable. All right, so maybe I just finish with some sort of consequences of this. So again, you have, given a irreducible holomorphic symplectic manifold, it has a moduli space of deformations of complex structure on that. And inside there, if you have a Lagrangian fibration, then inside the moduli space is a codimension 1 locus of deformations for which the fibration it's still a Lagrangian fibration. And generic point of that. So maybe I'll just mention one result which would follow from this. It's kind of, I mean, the reason I think this is an important conjecture is that it's easier to prove things when you have some control over the singular fibers occurring over here. I mean, once you get down to this, delta naught, that's codimension 2. You can generally avoid codimension 2 things when you're trying to argue geometrically, but you can't avoid the generic singular fibers. So you need to have be able to say something about how they look. And so this is saying that they're, I guess, as simple as you could hope for. So if we're in this situation, so let's assume semi-stable singular fibers. Okay, so from now on I'll assume this. Then what are some consequences of this? I just mentioned one result. So one of the things you can do is calculate the degree of this discriminant locus, this delta, as a hypersurface in Pn, in terms of topological information of X. So if the fibers of the Lagrangian fibration are principally polarized, okay, so what does principally polarized mean? So a principal polarization of a n-dimensional abelian variety is an ample line bundle on A. So this is a n-dimensional abelian variety. With such that it has a unique section up the scale. So, okay, so this is a definition of a principal polarization on an abelian variety. Okay, so then so if you have a Lagrangian fibration on one of these and you have principally polarized fibers, so an example of principally polarized abelian varieties are Jacobians of curves. Okay, so then the degree of this discriminant locus is given in terms of some topological information on X. Okay, so this is the A hat polynomial, and then I take, as a formal series, I take the square root of that series. And so altogether here, this is just some characteristic number. So this is some Chern number, which you can write out. So this is just some topological number associated to X. And then we can also write down a similar formula in non-principally polarized cases involving the polarization of the fibers of the discriminant locus. Also in the for principal polarizations, the degree is at least 30. And so more generally for a non-principal polarization. So for families of abelian varieties, polarization would be given by a pair of integers d1 and d2, where d1 divides d2. Okay, so for non-principally polarizations, there's these pair of numbers are bounded as well. D1 are bounded. So all of these results are trying to restrict the possibilities you can have. I mean, in the end, what we have here is a family of n-dimensional abelian varieties over Pn. There's some polarization on the fibers, and so these results are all sort of aiming to say that that the degree can't be too big, the degree of the discriminant locus can't be too large or too small, or the kind of polarizations you can get on the fibers are restricted in some way. And ultimately, once you narrow things down enough, you'd want to say precisely what the fibration looks like. Once, maybe if you have principal polarization, you could say it's exactly this space. And there are some other results in that direction, but I'll finish at this point.